All right, good morning, everyone. This is Adrian Jensen with Applied CAX. Thank you for coming to our technical seminar. Today we are going to be talking about hex meshing, and I have my staff member, Jeffrey B, that's going to be presenting. But before we get into that, just a bit of housekeeping to talk about here. First of all, something very exciting coming up next month is our Simcenter Symposium up in Seattle, Washington. This is going to be a full day all about simulation. We've got Femap, Simcenter 3D, Star CCM. We've got our staff members presenting. We have guest speakers and some of the team from Siemens at Star and Femap. So this is going to be a great event. You can register on our website, and I highly encourage you to join us. It's going to be a lot of fun. The other thing that we have coming up soon is our Simcenter Femap and Nastran training. This is another thing you can register on the website for. We've had new users, people with 10 years of experience, a wide variety of people get really useful stuff out of this class. It's something that we continually evolve and try and develop and improve each time we do it. So if you're new to Femap, or a longtime user looking for some new workflows, some tips, some tricks, some ways to get faster, this is another thing I encourage you guys to join. This is going to be, I believe we're setting up 2 weeks, half days. This is going to be a web broadcast style training. So it seems to work out well with schedules, work schedules. You don't have to commit to a full week gone. And it helps distribute some of the content over a little longer time span. More information on our website. Okay, so let's get into the seminar. If you haven't done one of these in the past, you will have, you'll see the little go-to webinar dashboard. You can go to the questions section, type in your questions there. I'll be online with Jeff and try to answer questions as we go, or we might take some pauses and respond to those questions live. This is going to be recorded and posted onto our website next week sometime, along with this presentation, this PowerPoint. So there's a lot of content in the PowerPoint. We might not have a lot of time for every single slide, but it will be posted online for you guys as a resource. So with that, let me introduce Jeffrey B, and he can take it from here.
Hi, my name is Jeffrey B, or Jeff B, and I'm a staff engineer here at Predictive Engineering. Thanks for joining us for our 998 Good Bricks seminar. Today we'll be discussing some hex meshing core concepts and efficient workflows. We'll be talking about what a hex or hexahedral element is, why you might want to use a hex mesh. We'll talk about some solid preparation tips for creating one. Adrian will jump a little bit into the Mesh Control Explorer, and then we'll finish up with some downsides and just some precautions about hex meshing and hex elements themselves. So to start out with, a hexahedral element, or a hex element, as everyone generally calls it, is a three-dimensional solid element. There are 4 different solid elements available in the NX Nastran library. I have them shown here just as an example. At the top, we have the hex. Note, all of these elements come in 2 flavors, linear and parabolic. You can see that the linear ones generally always have fewer nodes, and the parabolic elements have additional node on the midpoint of the edges. Solid elements are used to model 3D structures, things that can't be idealized with plates or beams. The hex element is the most commonly used solid element in the Nastran library, and for the good reasons that we will discuss. Tet and pyramid elements are mainly used for mesh transitions and in areas where hex elements would need to be excessively distorted to fit the geometry that you're trying to model. Here's some additional detail on the hex element. I don't want to cover everything on this slide, but it will be included with the seminar upload for later reference. The key things to remember here are the linear version of the hex element has 8 corner nodes. The parabolic version has 20 nodes. An extra node is added to the middle of each of the 12 edges. And finally, like all solid elements, it only has translational degrees of freedom at the nodes. No rotational degrees of freedom are used to define these elements or solid elements in general. So why use a hex element? The accuracy of the hex element is one of the primary reasons to use them. Here we are comparing the closed form solution for a deflection of a cantilever beam with a concentrated load at the end to the numerical results generated by first beam elements, then the 8-node hex elements, which are the linear elements, the 20-node hex elements, which are the parabolic elements, and finally the 10-node tet element, which is also parabolic. I didn't bother including the linear 4-node version of the tet element. The Nastran user's manual states very clearly that you should always use the 10-node tets for all structural simulations whenever you're solving for displacement and stress. The 4-node tet is overly stiff for these applications. In general, you should minimize your use of the 4-node tet element, especially in areas of high stress. Okay, as you can see, the simplest beam element does an outstanding job matching the closed form solution. I have a number of elements, beam elements shown there, but really you'd only need one. The beam built of 8-node hex elements comes closer to the closed form solution than a beam built with over 50 times the number of 10-node tet elements. And finally, you might find this a little strange, but the same number of 8-node hex elements outperform the same number of 20-node hex elements using less than 1/3 the number of nodes. How can that be right? Well, a minor side note. There is a lack of practical value in using the 20-node hex element because in most situations, the same accuracy can be obtained with the 8-node hex element due to the addition of enhancement functions. Enhancement functions, specifically the Wilson incompatibility shape function and a function that alleviates volumetric locking, are added to the element formulation to improve its performance. Of course, there is a minor cost associated with these, computational cost, but the cost is on the individual element level and does not increase the size of the global system of equations. This is because no additional nodes are added with these enhancement functions. And for this reason, these elements are ideally suited for implicit analyses where the time step can increase more rapidly with more accurate results. So continuing on accuracy, hex elements exhibit superior performance in bending and torsion. Tet meshes also inherently have poor aspect ratios because the internal angles of a triangle are typically more acute than those of a square. The nodes also have high valence, which is just another way of saying each node has more connectivity, which artificially increases the overall stiffness of the finite element model. You can see that one node can have up to 3 elements contributing values to it. Finally, hex elements do not suffer from non-physical stiffness due to mesh locking to the same extent as equivalent tet meshes for large deformation and nonlinear elastoplastic structural analyses. Came across what I thought was a good way of visually conveying the concept of mesh locking, and I have it shown below. The areas of the triangles must remain constant if the material is incompressible. In triangle 1, if node 1 and 2 are fixed and the height of the triangle must remain constant in order to keep the area the same, node 3 can only move left and right. Similarly, in triangle 2, node 6 can only move up and down. If these triangles are combined in a mesh, node 3 in the resultant mesh becomes fixed. The element's nodes cannot move, which is what we call locking. An analogous problem occurs in 3 dimensions with tetrahedral elements. And you're going to see this a lot in the corners, in sharp corners and right angle corners of meshes with these kinds of nodes. And this is kind of an example of why you might see that. Another advantage is their layered structure facilitates stretching in the row or column directions without degrading the numerical quality of the element. In broad terms, this is because the numerical quality of elements is dependent on their corner angles. Corners do not change when a square is stretched along one of its side directions, whereas the corner angles of a triangle, no matter how it is oriented, become adversely large or small when the triangle experiences large amounts of stretching or deformation. And finally, we can talk about speed. It takes 5 tet elements to occupy the volume of a single hex element. As discussed, tet elements really do need mid-side nodes to produce accurate results. This means those 5 tet elements must be 10 node tet elements, and the resulting cube will have 26 nodes total. These additional nodes just add computational time. They don't improve the accuracy of the result. Okay, now we're going to get into how you create a hex mesh. There are 4 really important steps to follow. And the first is most of the geometry that you're going to work with will not easily lend itself to being hex meshed. So you are going to have to subdivide your model into hex meshable parts. You'll then determine an appropriate hex mesh size. You'll verify with the software that all of the components are hex meshable. And finally, you'll verify element quality. So these are the steps, and we're going to run through these in the software today. So first, let's just talk a little bit about the anatomy of preparing a solid. So Femap can only hex mesh extrudable or sweepable solids, and that includes revolvable solids too. If your part is complex, you must slice it into simpler solids that can be hex meshed. And like I said, you're probably not going to be dealing with a lot of parts that are hex meshable right out the gate. Femap can mesh solids where it can easily identify a base and a top surface that are connected by 4-sided surfaces. You can see that on the right. The base and the top surface can be of any shape and can also include holes. The base and the top surface must have the same number of edges. And finally, the base and the top surface must produce a mesh with the same number of nodes, elements, and connectivity. The elements can differ in size, and we can see that here. So, in the first solid, Femap cannot identify, or the first solid is non-hex meshable. And so here we're going to talk a little bit more about the mechanics. We can subdivide this non-hex meshable solid into 3 solids that meet the hex meshing prerequisites. The base and the top surfaces must have the same number of edges. The base and the top surfaces are connected by 4-sided surfaces. And the base and the top surfaces must produce a mesh with the same number of nodes, elements, and connectivity. You can see the bases and the tops are not the same size or even both flat in the case of the little cutout with the circular top. Those are not mesh or hex meshing prerequisites though. Once the base and the top are meshed, you can see that the meshes on these surfaces match. The elements are just different sizes. So if you look closely, you can see that all through the structure, the mesh is identical. The elements are of just different areas. Okay, so the side surfaces control the mesh along the length of the extrusion or sweep. There must be a single path through the lateral surfaces from each edge of the base surface to a corresponding edge on the top surface. And so you can see there on the left, you have 4 edges on one face. And then on the right, you can see that from base edge number 3 to top edge number 1, there can only be one path that the mesh can follow. And that's going to allow this part to become hex meshable. Okay, so moving on. Here we have the 4 examples that we're going to talk about today within the software. We have this 3-sided, or we have 3 5-sided surfaces here. We have a cube with 2 holes in it. We have this much simpler one which just has a split in the top, and then we have a partial depth hole that's not embedded. And so let's jump in. These slides will kind of highlight what we're doing, but we're going to do it in the software. So I'm going to switch now to Femap. Okay, so here we are. Here's our hex meshable or unhex meshable solid. the first thing that we're going to do is slice it up. One of my favorite tools for doing this is the solid slice with a plane. And so I'm going to go ahead and start there. First, I'm going to pick front. Okay, so the first thing I'm going to do is select the solid that we want to slice. Okay, and then my favorite way to use this tool is to use surface normal instead of locating, but anything really works. I'm going to select this surface here, and then I'm going to slice it at this point. But I don't want to slice it right at this point, or I'll end up with a geometry similar to what I have now. And so I'm going to move that point up. So I'll use the offset button here, and I'm going to offset it by 2. And then I'm going to preview that just to make sure that my offset's in the right direction. It's not in the right direction, so I'll offset it by -2, and that looks right to me. And so I'll slice there. Okay, now we can check and see that. Okay, if we go to modify or mesh control, size on solid, and I just select this one, I can see that this solid is going to meet the hex meshing prerequisites. The top and the bottom surface are the same. It's connected on all 5 sides by 4-sided surfaces. So this should have no problem. So I'm going to go ahead and put a size on solid. I'll say I'll hex mesh it. I'll bring this down to 0.75 and say OK. And sure enough, it highlights itself blue, meaning that it is hex meshable. The red is not hex meshable. Okay, so I'm going to take that and I'm going to hide it. And you can see this is exactly the same shape I had before, without the sphere coming all the way up to vertical. To create the 2 hex meshable solids out of this piece, I'm going to use the slice with curve feature. Slice with the curve. I'll hit slice with curve. I like to choose vector direction so I know exactly which direction it's heading in. Along normal, curve normal also generally works, but you know for sure based on your orientation if you use vector direction only. So I'm going to select that. I'll select my solid again. Now it's asking me to select the curve to slice with. I'm going to select that arc right there. And then now I'm going to define the vector that I want to slice with. And I didn't reset my cube here, so I'm going to really quickly, there it is. Okay, so I'm going to run through that again really quick. I'm going to slice with curve, vector direction, okay, select my solid, okay, select my curve, okay, and then I'm going to slice, or my vector will be in the -y direction. Okay, now I have my slice, I have 2 solids here, and both of these solids meet the hex meshing prerequisites. So I'll bring my top piece back. I'm going to mesh control, size on solid. I'm going to select all, hit OK. I'm going to hex mesh. I'm going to drop this size down a little bit, just on 2.75. Because we're using a hex mesh, it's going to be fast and accurate anyway. And so, okay, now my whole solid is blue. And these opaque surfaces between the various solids indicate that those surfaces have been matched. And they will generate similar meshes, or identical meshes, not necessarily with the same element size. Now I'm going to go to Mesh, Geometry, and instead of solids, I'm going to go Hex Mesh Solids. Again, I'm going to select all of my solids, hit OK. In this, I use the defaults, merge nodes on match surfaces, and then hit OK. And there you have it, a hex mesh solid. Of a hex mesh on a part that before slicing was not hex meshable. I'm going to now go ahead and check the element quality. This is another thing that is a very important last step in these processes to make sure that you get something good. And you can see here I've contoured the Jacobian value. and I have a maximum value of 0.61, which is not terrible. I'd definitely run with a value like this, especially with these kinds of elements. Okay, so that's our first example. It's relatively easy, but let's move on. This one I found quite a bit harder, and it took some thought, but following the guidance, or at least meeting the criteria for what it needs to be hex meshable, it is totally possible to hex mesh this part. So the first thing we're going to do, again, I'm going to use solid slice with plane. I'm going to select my solid and say OK, and then I will use the bottom surface. I will slice it at this point, but I'm going to offset that down so that you'll see in just 1 second when I cut that. I'll offset it down by just 0.5. Let's preview that, make sure it's in the right direction. Okay. Okay. So you'll now recognize that this part is definitely hex meshable. It can be extruded from, this would be the top surface, this will be the bottom surface, and it can be extruded up. So just to double check that, we'll go to mesh control, size on solid, select this solid, hit OK, hex mesh, hit OK, and sure enough, it does highlight itself blue. Okay, so I'm going to get that out of the way, and now we're going to work on this part. So to make this a hex meshable part, I look at this and I see two big rectangles here that could be extruded down, and then I see this surface which could be a top surface, and some surface here that could be a bottom surface, because I know that my top and bottom surface can have a hole in them. So I'm going to create some more slices. I'm going to use solid slice with plane, select this one. Okay, I'll use this side plane. I will select this point right here. I don't need to offset that at all. So there's my first slice, and I can now see the top and the bottom of the middle portion becoming hex meshable. I'll do the same thing on the other side. Select the side. I'll select this point here for the location of that slice, and hit OK. Okay. This should be hex meshable. I have two parts on each side that are perfect extrusions of a rectangle, and then I have a top. Even though this space is curved, it doesn't matter, and I have a hole in the middle. So now I'm going to mesh controls, size on solid. I'm going to select these three solids. Okay, and hit Hex Meshing. I'm going to take this down to 0.65. Oh, okay. So I've forgotten to do something. I can see here my two side pieces are good to go, so I'm going to remove those. And that brings us to our next point. This surface, it cannot. The problem it's having is it's not matching this top surface to this bottom surface because of this curve. So what I'm going to do now is remove that curve with the feature removal tool. I'll just remove them one at a time. And there. Now it should recognize those two surfaces. I'm also going to just clean up these points. I'm not sure that really matters, but it'll only delete the points it doesn't need. It removes some points on the ends there. Okay, now let's try that again. So I'm going to size on solid, select this part. Okay, Hex Mesh. I'm going to bring this down a little bit just so that we start getting a reasonable mesh out of the gate. Okay, and it now appears to be hex meshable. I'll bring everything back. I'm just going to make sure that I have the same size on everything. So I'm going to mesh control, size on solid, select all, okay, hex mesh. I'll do 0.65 for the whole thing. And now, again, I'm going to mesh, geometry, Hex Mesh Solid instead of just solid. Select all the components, hit OK. And we've got a hex meshable part. Let's quickly check the Jacobian value really quick. And we can see it's not terrible. 0.77. It's getting up there a little higher. There's some minor tweaks we could make. I think, we could come into mesh surface. We could turn a map mesh on. This will be the same size that we were going, 0.65. And then let's just see if we can do this. The best thing to do, actually, I'm going to take that back. I'm going to turn this mesh off. I'm going to slice this piece up one more time, just to give it some more guidelines for the meshing process. So I'm going to slice with part. I'm going to slice with surface again. I'll use this surface here, and I'll slice at this point here, hit OK. And that's just going to give it some more barriers for which to align a good mesh on. All right, so let's, again, one more time, size on solid. I'm going to select all of these ones, take it down to 9.65, and then I will mesh, geometry, mesh solid, select all. Okay, I'll delete my existing mesh and go for the new one. Okay, you can see that has dropped me down to 0.65, which is better than what we were at, and it's looking pretty good.
Can I hop in on one thing here? So let's turn off the elements, because one of the things that catches people up is looking at these opaque surfaces, and these show what's matched up. So the most recent slice Jeff did really helped out with the element quality of this central piece, but we want to carry that slice through to its neighbors so that the side rectangular piece has surface matching with the central pieces there. So even though this creates a good mesh, it's good to come back and take a look at the opaque surfaces to see what has matched together. And once I get into the Mesh Control Explorer, I'll show you guys some other ways to double checking that.
Thanks, Adrian. Yeah, so let's just quickly do that, and let's see what happens. So we'll do size on solid again, select all, Hex Mesh, come down to 0.65. And yeah, that's just adding more, you can see again, all those surfaces have been matched up, and it's just giving it more information to size the mesh on well. So Hex Mesh Solid, select all, okay, delete. Look, all right, I'm having a little bit of, we'll come back to this.
Yeah, we just have to delete the mesh.
Yeah, okay. So the one thing I did want to really quickly show is I just wanted to show this with a TET mesh as well. And so this is a TET mesh. The recommended size was over 1 unit, and I brought it down to just 1 unit. And you can see here that this mesh has also a Jacobian of, on almost 0.7, and it's got 8,000 nodes. Whereas if we come back to, I'm going to go to my 2-hole finish one. This one has only 4,000 nodes and a Jacobian of 0.6. So this is a much smaller problem. It's about half the size because it has half as many nodes, and it has a lower Jacobian, which is another way of saying it's got higher element quality. So I just wanted to show the difference between a TET mesh and hex mesh. These elements are larger, but they still have twice as many nodes. So you can use smaller elements with a hex mesh and keep the problem small. So, all right. And then the final example I wanted to show is just a partial depth hole. This one again is pretty easy, but this one is done by embedding a face, which is you could slice with curve or you could embed a face. And I just wanted to show, like, initially this is not hex meshable. Then this way we can use a different tool. We can say geometry, solid, and then we can embed face. And if we embed face, we can pick the face that we want to embed. And you can see right now there's nothing on this side. We can embed that face through the solid, hit OK. You can use the defaults here again, automatic, outline only, okay? And now again, I have two solids with that face embedded on the other side. And again, this should now be hex meshable because it has tops and sides connected by four-sided surfaces. In the case of the cylinder, it's got a single surface connecting it, which also meets the criteria. So let's try with the mesh controller, size on solid, select both, hit OK, hex mesh, take this one down to about a little less than half that size, 0.08. Then we'll hit mesh, geometry, hex mesh solid, select both parts, hit OK. Oop, I forgot to add a material, so I'll do that really quickly. Okay, and here you can see this was not hex meshable, now it's hex meshable, and most of the elements are going to be of great quality. So let's just check. Have a Jacobian, 0.6. So again, this is a good mesh. It'll run really quickly and it'll give good results. Okay. Back to the presentation. So we covered these three solid preparation examples, and we use the various slicing techniques. I think slicing with a plane or slicing with a curve are really efficient ways of creating these hex meshable solids. If you keep those three prerequisites in mind while you're doing this, it's kind of entertaining to look at a complex piece of geometry and say, okay, do I have a top face? Do I have a bottom face? Are those faces connected by four-sided edges? And is there a single path through those edges? And if there are, you're going to be able to generate a hex mesh on that solid. And like I said, that's going to lead to good things as far as results and accuracy and speed. So again, these will just be up on the web to kind of show you where I sliced. Here I removed that parting line on the surface before I stopped. Here you can see I've just identified the various components of these parts. And again, here I'm just showing, you can see that the base and the top meshes are identical. They line up, and then when you put them together, they also line up because those surfaces have been matched. I am now going to turn it over to Adrian, who's going to kind of discuss, or not kind of, he's going to discuss the Mesh Control Explorer and how it works, and then we'll come back and talk about some of the downsides of hex meshing.
All right. You go ahead and mute, and I will carry it on from here. Okay, so Jeff has done a great job of the core skill sets of hex meshing here. But I want to talk about some of the newer features that are making it a bit easier. I've got a couple of different example pieces of geometry here, and you may have recognized these from our Femap class or previous seminars. All of the hard work of slicing and dicing is already done. So these are hex meshable geometries. But I want to show you some of the new features and how they help things out here. So same routine here, size on solid. I'll select everything, go for hex meshing. We get this confirmation here that things are matched up, both in the message window. You can see this linking of surfaces, and also with the updated color on the surfaces here. So this is a nice way to see things. Once we go to mesh this part or these parts, see a nice hex mesh on here. Now, one of the things that has traditionally been a problem with hex meshing is updating the mesh after it's been created. The meshing toolbox over here on the left has always been really useful for surface models, even Tet Mesh, but Hex Mesh, it was a bit finicky. Usually you had to do all of your sizing before you mesh the part. Now there's a new feature in Femap called the Mesh Control Explorer. This is this window pane here. If you don't see that, you can open it up with this little green block in the meshing toolbox. That will be its own window pane. And let me resize this, it's a bit easier to see. This is basically one spot that allows you to view a bunch of different mesh attributes or mesh controls. Well, the one that we're particularly interested in is showing our matched surfaces. So while each surface has a match in the hex meshing, whether it's the base and the top of a single solid, or whether it's two adjacent surfaces of matching solids, this all uses surface matching. And rather than just seeing by colors or having kind of a rudimentary visual check, this allows you to see things one by one. It also allows you to see the daisy chain of linking between one surface to the next and how it will propagate through the model. So this is really nice because we have a new sort of bookkeeping tool for our hex mesh to see what's linked to one another. Now I'll park this back over here and let's modify the mesh. So when I do the meshing toolbox, let's go with mesh sizing. Let's say I want 2 elements through the thickness of the web and the flange of this. When I click one of these curves and update that mesh size, you'll notice that that mesh size propagates through all the way. So the meshing toolbox is now working for hex mesh much more similar to the way it does with plates and tets. And you can see I can easily kind of come through and update. Some of these are mapped surfaces and it automatically propagates through. Sometimes I'll need to set an additional element size on all different sides. But the nice thing is I don't lose any connectivity of my different parts here. One of the ways I like to check connectivity between hex mesh parts is turning off all of your geometry, just looking at the elements here, and we can use transparency. This will help us show any free surfaces. It looked like maybe in here we've lost some connectivity. I might have to merge my nodes again. The other one that I use is the clipping plane. And the clipping plane, let me set this on the model. The clipping plane really only draws free surfaces of your model. So when you slice through a solid mesh like this, you'll be able to see potential free surfaces, which would indicate some sort of nodes that have not been merged. So here, when we peek inside, it looks all hollow because it's only drawing those free surfaces. As we come over to this region here, there's a little bit that didn't quite get merged in with the rest. So this is better than it used to be, but you can still see it's important to know some tools to check your mesh and merge your nodes. A few other example geometries that you guys have probably seen before, but are quite useful, is this part here. So this is one of the assemblies in the Femap examples. As you can see, it's already been split up into different pieces, but let's just run through this routine one more time. Hex meshing. I don't need a material. This is just a meshing example. There we go. So it's all hex meshable, but now with the Mesh Control Explorer tracking all of these linked surfaces and communicating with the meshing toolbox, we can update sizes on one curve and watch that propagate through. I also really like under mesh surface being able to update the mesh approach. So let's go for a mapped mesh. I'm not going to adjust any sizing. I'm just going to set a mapped approach on something like this surface here. And you can see it maps and projects through. So a lot more of the meshing toolbox features are available for you. And yeah, just a quick kind of exploration there. All right, Jeff, let me pass it back to you.
Thanks. Okay, so back to go into the presentation a little bit more. So what are the disadvantages of hex meshing? And the major issues with hex meshing are aligned with what Adrian was just showing. Like fully structured hex meshes, they are notoriously difficult to generate, and that's manually or with an algorithm. You saw it actually took a lot of us going in and turning the geometry and finding, finding our top and bottom surfaces and finding ways to slice them up so that we could, you'd have four-sided surfaces connecting them. And that's not trivial, especially in some of the harder parts. It usually can be done, but it can't always be done. And then for an algorithm to do it, it's become incredible. They've found it's very difficult. So there's a joke that an automatic boundary conforming all hex automation has been dubbed the holy grail because it's so difficult but so desirable to achieve, just due to the speed and accuracy of the hex element in general. As Adrian was showing, things are getting a lot better, but in general, hex meshes are fairly inflexible. Like a local modification in one area is usually going to necessitate changes to the mesh in adjacent regions, which tends to cascade across the entire model. And so before, if you made changes in the hex mesh in Femap, it wouldn't necessarily propagate them through the matched surfaces, and you'd end up with a lot of issues and a lot of problems. And it's getting better and better, but it doesn't work 100% of the time. And like I said, you can't simply add refinement in one area and not have it need to propagate through to everything that's touching it. This makes hex meshes ill-suited for mesh adaptation methodologies. So if you're asking the software to refine the mesh as it identifies high stress regions or all these optimization tools, it's going to have a really hard time doing that with a hex mesh because it won't be able to. It'll have to refine the entire model, and it won't be able to just refine the local areas you're interested in. This is not a problem that TET meshes suffer from. And then the fact of the matter is, TET generation technology is fully mature nowadays, and there are numerous push-button algorithms capable of quickly generating meshes that adhere to size and geometry requirements and that are of really good quality. The element formulations for parabolic TETs are very good and are producing very good results, even if they're not quite as good as hex meshing or the hex element formulations. So, for a lot of reasons, it is just easier to use a TET element or a TET mesh than an equivalent hex mesh.
Mind if I hop in on that? So a lot of the ways I think about this is how you allocate your time. If it's a linear run, you're only going to be doing it a few times. You're not that worried about solve time. So save your time with easy push button TET meshing. If you've got nonlinear dynamic runs, something you're going to be doing lots of iterations, lots of runs, and you want that solve time to be as fast as possible, invest your time up front with a hex mesh. Each problem you kind of have to choose where you want to allocate your time. So the holy grail, as we say, but there's still a place for the auto mesh or the tech mesh.
Yeah, and just to elaborate on that, since we have a little bit of time, you know, in an explicit analysis, your time step is going to be dictated by the quality and the size of your worst element. And in general, a TET is going to have a smaller effective size, and will decrease your time step and make your run longer. So, like Adrian said, if you're going to be running a lot, or if it's a long implicit or explicit analysis, a good hex mesh will save you a lot of time in the long run. With implicit analyses, if your results are more accurate, you'll be able to take bigger steps through time. Your convergence will be faster. And so there's another situation in which if you want to spend the upfront time creating a high quality hex mesh, you'll probably see the dividends in run times with that implicit analysis as well. So those are two major reasons for using the hex mesh. The last thing I really wanted to show was a more complicated example of just the varying, just one more compelling reason on a more realistic part. This is an automotive hook, for example. We're using half symmetry here, and you can see the results here are almost identical. You really can't tell the difference. The only difference between these two parts is speed. And you can see on the left with the hex mesh, we have a really nice structured hex mesh. And it's on the right, you have a similarly sized TET mesh. And the difference in the max von Mises stress is 0.2%, so essentially no difference in stress. The difference in runtime for these two parts is 650% different. The hex mesh runs in 36 seconds. The tetrahedral mesh takes 270. Now, again, that might not seem, you're going to spend more time dividing this part up than you'd save, unless you're going to be doing this many times, or it's in a situation where you'll need to do this or run it again and again and again and again. The reason it's so much faster is the node and element count. Every node will have a component in the stiffness matrix, and when you add 617% more nodes, your matrices get much, much larger, and it takes the computer much longer to solve those systems of equations. And so, yeah, I just wanted to really highlight the speed and the fact that you're really not suffering accuracy losses for those gains in speed at all.
Right on. So we have a couple of questions. The one I thought was probably on a lot of people's minds is, what about the 3D hybrid meshing? So the most recent versions of Femap have come out with an auto hex mesher, which does not require your geometry to follow all the rules of a clean base and top connected by four-sided surfaces on the edges. And we didn't really get into that too much because we think it's much more important to understand these core concepts, the pros, the cons, and the skill sets to do it traditionally, because the auto mesher is exactly that, it's auto. It doesn't require skills or techniques, but the knowledge that Jeff has covered during the seminar is going to help you understand why you may or may not want to use it. So it's not always going to automatically give you full hexahedral elements through the entire structure. It's going to be mostly hexahedral elements. There's going to be certain parts of your geometry that are not hex meshable, so it might use tetrahedrals. And then to transition between the two, it's going to have to use wedges and pyramids. You're also working with a mix of linear and parabolic. As Jeff mentioned earlier, the tetrahedrals, you have to use parabolic, you have to use mid-side nodes. The major advantage of hex is reducing our node count, so you really want to work with the linear version. So then you have a mix match of some elements with mid-side nodes, some without, some tet, some pyramid, some hex. And you want to look and see each of those in the structure where they lie. You don't want those odd elements in your high stress region or a region with a high stress gradient. So we encourage you to explore this tool and try it out. It could really save you some time. I think the geometry we see here on screen would probably hex mesh quite cleanly with the auto hybrid mesher. But I've seen plenty of others that I would just rather use a tet mesh, knowing that I have a consistent element type and no transition regions in areas of concern. So use some of the knowledge covered in this seminar to scrutinize the mesh that those automatic tools can give you. But that being said, it does have its advantages in terms of creating things quickly.
And I could just add, if you do use that automated generation and then decide to keep your mesh uniform by making all of the hex elements parabolic, then you kind of lost the advantage of using that tool in that you increase the size of the problem dramatically by using the 20 node hex element over the 8 node hex element. And again, you haven't really improved your accuracy by doing so. So adding that, changing all of the elements to parabolic and using the automatic hex mesh generator, they kind of fight each other a little bit.
I see we have a few minutes left. Maybe let's pull up one of your two-hole example, what the auto hex mesher does to it.
Yeah, that's a good idea.
So while Jeff pulls that up, I'll just remind you guys that this is recorded. We'll have it up on the website next week, along with the presentation, all the material. We've got plenty of other seminars on the web there. So if there's any of the other tools that we're using today, like the draw erase toolbar, or some of the visualization options that we didn't really discuss, check out our other recent seminars and those can help you out. So this is the new Hex Mesh Bodies option here. You can see it's kind of got its own section on the menu, and it doesn't use a fixed mesh size. It gives you a target element size. So where the traditional mesh sizing will put nodes on points and along curves and follow your sizing quite strictly, this one is going to aim for the target size but adjust as needed. It'll also not necessarily associate with all geometry. You have that option, but it might ignore certain points or curves or small surfaces if it helps it get a better mesh quality.
And interestingly, it is defaulting to adding the mid-side node on the hex elements. So you're going to be getting 20 node hex elements when you do this, which begs the question of why you might want to do that. The 20 node hex element still has 6 nodes less than a cube made out of tetrahedral elements. So you are getting a 30% advantage in node count by using the 20 node hex over a pure tet mesh. So that's one thing to consider. Should we show it on or off?
Yeah, let's just go all defaults here. Let's see what. And the good way to investigate this, or the way that I like, is from the model info tree. And up at the top under model elements, we can look at type and shape. So everything ended up with mid-side nodes using the defaults, so everything is parabolic. But under shape, you can see the individual brick or hex, wedge, and pyramid. So if we turn off our bricks, maybe let's turn off our surfaces as well. You can see that this isn't so bad. I guess maybe if our high stress areas were around the openings, which is likely, because that's a likely stress concentration, this might be a concern. But it's definitely dominantly meshed with bricks. There you can see our transition pyramid and tetrahedral elements. And then when we hide the pyramids, those are just the tets there. So everything with a grain of salt. Sometimes this tool works very nicely. Sometimes it doesn't. but it's all about investigating the resulting mesh that you get.
That one has a good Jacobian.
Yeah. I don't know. That's the body measure. All right, let's see if we have any other questions, and then we can wrap up. So if you can drag down there, checker bar. All right, so we've got a lot of questions about the hex mesher. All but bricks. Yeah, exactly. Some of you were commenting on using all but bricks, so that option is there for the Hex Mesh Bodies tool to turn off mid-side nodes on bricks. That's going to help out with your node count quite a bit. And what do we have? I think that kind of covers it. A few questions just about the software. We're working on 2022. I believe 2022.2 is about to be released.
Actually, this is 2022.2. It was released at the very end of April. And
okay.
So,
yeah, if you guys want to be on the latest version of the software, I'm not sure if the dot releases require a license update, but you can contact us on the Applied website if you're one of our customers, and we can get you all set up there. I think other than that, we've sort of covered everything, and we're wrapping up on time. So thanks again for coming. And just another quick reminder, we do have our symposium coming up next month, June 17th, I believe, and Femap training coming up as well. So check into the Applied CX website for more info on those, and hopefully we will see you there. All right, thank you very much.